With this lecture, we're going to kick off one of the most important parts of the course. We're going to work our way through a bunch of classic problems in the area of data structure design. For example, designing hash tables, designing binary search trees, other things like that. And they're all solutions to these classic problems that were posed decades ago and solved successfully. And what we're going to do is do it ourselves. And the reason is we'll get a sense of how these problems are solved and the different trade-offs that come out of the design process and out of the end result. So today, we're going to focus on a bit of a more obscure data structure than those other ones you may have possibly heard about. And this one's known as the disjoint sets or union find data structure. And it's used to solve a problem known as dynamic connectivity. And I'll get to it in a bit. Now, the reason we're going to do this today is we're going to see how a basic data structure design can evolve from relatively basic, slow performance, up to a more sophisticated, much better performance implementation. We will also see how our choice of the underlying abstraction that we're using in our data structure can make a really big difference in how our code complexity expands and also the performance of our data structure. Now, what I mean by that is disjoint sets is going to need to do a certain thing, and the choices that we make back here as monks, like the basic idea, let's use a fire that casts shadows through some objects we hold in the air, will deeply affect how difficult it is for us to showcase what the users want to see. Okay, so let's jump into what the disjoint sets data structure is. So it has two operations. The first is connect, which connects two items. And the second is connected. And it returns if two items are connected. Now, connections can either be direct or they could be indirect, that is, the result of a bunch of transitive connection operations. So for example, let's suppose we connect China and Vietnam in our data structure. And then we connect China and Mongolia. And then we ask, is Vietnam and Mongolia connected? Yes. Well, the answer is they are indeed, because we have a transitive set of connections. If we then say, let's connect the USA and Canada, and then check whether the US is connected to Mongolia, the answer here is false. And you and I can see that visually, but we're going to be building a data structure in a computer that can solve that same problem. Now, the answers can change. So, for example, let's suppose we connect up China and the United States. In that case, if we now ask if the United States and Mongolia are connected, we would say true. That's it. That's all we're going to do today is build this data structure with these two very simple operations. Now you might say, why would I ever want this thing? And it turns out that this is useful for many purposes. One of them is in the natural sciences, somewhat surprisingly. So there's an area known as percolation theory. Actually, this also comes up in pure mathematics and applied mathematics. And one of the most interesting examples that we'll actually see in the homework in this class is a computational chemistry problem that this data structure will enable us to solve. It's also useful as a basic building block for other algorithms. For example, an algorithm we'll talk about later in class known as Kruskal's algorithm. So it turns out to be a generally useful thing. So I'm going to simplify the problem just a little bit in order to make it just simpler to think about. There's no loss of generality here, but what we're going to do is we're going to force all of our items to be integers instead of arbitrary data. So we can't just connect USA. We're instead going to say connect up 8. Okay? So all my items are going to be all integers. And then secondly, we're going to say that everything must be declared as existing in advance. So I'm going to, for example, say I want a disjoint sets object of size 7, and everything will be disconnected at start. And then after I connect up 0 and 1, 1 and 2, 0 and 4, 3 and 5, we end up with this topology. Now, just as we saw in the USA, China, Mongolia, Vietnam, and Canada example, we can now call, say, is connected, and say, are 2 and 4 connected? Yes. Are 3 and 0 connected? Nope. And just as before, we can connect things up. Let's connect 4 and 2. Okay. Let's connect 4 and 6. Let's connect 3 and 6. Hooray. Now if we go through and say, are 3 and 0 connected? The answer is now true. Okay. So, how do we make this thing? What's it going to look like? Well, I do want to address the issue of we're going to ultimately be rewriting Java code. And so the interface we might have in Java would be something called disjoint sets that has a connect and an is connected operation. And now our goal is to actually build the specific implementation of this disjoint sets interface. Now we have to keep in mind a few things. One, the number of elements in our disjoint sets object right here could be potentially huge. Let's say millions or maybe even hundreds of millions. And the number of method calls can also be huge. So it won't be good enough just to do some brute force thing. We're gonna have to be a little more clever. And we also need to keep in mind that the calls to the methods can be interspersed. So it's not like someone's gonna do all the connections first and all the isConnecteds first. And that would actually result in an easier data structure. But because we have to deal with dynamic connectivity, that is, it can change over time, it'll change the way we approach the problem, as we'll see. So let's start by considering just a naive approach as to finish our setup. And in this approach, what we would do if we wanted to connect two things is we would record in some kind of data structure all the lines connecting every individual connection. And then when we called isConnected, we would do some kind of iteration over the lines. Like let's say we did isConnected 0, 5, we would do some kind of maybe recursive thing where I look at the neighbors and then do something, but I'm actually going to stop us right there. This is too much. And I'm going to make a really important observation that's going to make our lives much better. Specifically, we do not need to actually keep track of each individual line, but instead we can keep track of only the sets that each line belongs to. Or sorry, only the sets that each item belongs to. So if I say connect 0, 1, at that point we go from everything belonging to its own individual set to now 0 and 1 being part of the same set. When we connect 1 and 2, we bring 2 into that set. When we connect 4, we bring 4 into the set. When we connect 3 and 5, these two sets are merged. At this point, the isConnected operation just says, are they in the same set? And it's a little different than what you might have tried to do naively, where you had all these lines you had to think about. This is simpler. So next up, if we connect 4 and 2, you can try and think about how the state of the universe changes. Turns out it does not. They're already connected. If we connect 4 and 6, 6 gets brought into the set. And when we finally connect 3 and 6, everyone's part of one big happy family, and all isConnected operations will return true. Right? So the big idea here was, if we only keep track of the sets that you belong to, then hey, the problem is a little easier. We don't have to write down the line. So the words that I have up here, connected components, are a typical name for this. And so to give us precise definition, for every item in our problem, its connected component is the set of all the items that are connected to that item. So 1's connected component is 0, 1, 2, and 4. And so the naive approach was recording all the lines, but the better approach was to model connectedness in terms of sets. And this is a big idea that will make our lives much easier. We don't care about how things are connected. We only care that they are connected or not. And that'll make our lives a lot better. So in the next video, we'll start thinking about how we actually do this in Java. But make sure this makes sense before you move on.